Hello, and welcome to the final part of Chapter 2, the final lecture covering Chapter 2. This is the fourth of 4 lectures that introduces motion, okay? The study of motion known as kinematics, which is Chapter 2 of the physics of everyday phenomenon, which is what this lecture series is all about. So we've been talking about acceleration. We led up to it with a discussion of speed and velocity, okay? All the study of kinematics. Now, we finished with defining acceleration. We know it's a vector. We know that it can point in a certain way in particular situations. We know that it can change when both the magnitude or the direction of velocity is changing or both is changing, okay? So all of that is wonderful in terms of a general definition, but what we're gonna have here is a workhorse of a particular situation, which is when the acceleration is constant. So the acceleration is just gonna be some fixed value, like 9.8 meters per second squared. Mentioned that a couple times, right? We'll see that more in the next chapter too. So it's just going to stay at that fixed value, okay? So with that in mind, we have a whole set of ways we can quantify that effect, that resulting motion, okay? All right. So uniform acceleration is the simplest form of acceleration, but still a really important one, okay? So it's not like we're actually missing the point here. It occurs when there is a constant force acting on an object, okay? That could be like a constant tension force. It could be a constant buoyant force. It could be a constant gravitational force. As we get into other types of physics, it could be a constant electrostatic force or magnetic force. But if it's constant, which means it doesn't change with distance, it doesn't change over time, okay? Then we have constant acceleration. Constant force, constant acceleration. Remember that, okay? So most of the examples we consider will involve constant acceleration, right? It really is ubiquitous. It's very common. Falling rock, okay? Car accelerating, right? So, passing someone. You assume they're going to be accelerating at a constant rate, which is, pretty accurate because you kind of like, you push, down the pedal a certain amount. You push that same amount throughout your moment of acceleration. Constant acceleration is pretty commonplace, okay? So the acceleration does not change as the motion proceeds. That's what we mean by uniform acceleration, or as I keep calling it, constant acceleration. Now, I think your book is a little loosey-goosey about this, which is fine, but usually uniform is the same in space, like x and y, right? Or z if it's three-dimensional, and constant is the same in time, okay? Now here, we actually want the acceleration to be both uniform and constant, and those terms can certainly be used interchangeably. The point is that it just doesn't change. Okay, throughout the system, the situation that we're describing, the word problem, no change, okay? The example, whatever. Okay, so for example, a car moving along a straight road and speeding up at a constant rate, right? So just like, maybe the pedal all the way down, so just that constant rate of acceleration would have a constant acceleration. So if we graph the acceleration, this is actually the second time we've seen a graph of acceleration. Both of them become weird. In the last video, we saw little spikes showing, sudden changes between velocity, okay? Sort of disruptions, if you will. Here, it's just a flat line because it's just a steady value, okay? It's just that constant force. So notice that even though the acceleration is not changing, the speed will be changing, right? Because you are, you're speeding up. Constant acceleration is still a change. It's a change in speed, okay? We'll see it's a linear change in speed, and it will create a square change in position. So we're actually going to end up with a parabolic displacement, okay, a parabolic position function. So in that case of the car accelerating at a constant rate, our velocity would increase at a linear rate, okay? Because remember, acceleration is just the change in velocity over time, okay? Therefore, the change in velocity, okay, so the delta v here, is just going to be equal to acceleration times time, okay? So think about that. Now, that's great, right? Delta V, if you had a general statement, because you could just say, oh, well, this is my change in V, it's equal to a times t. And then you can't do too much with that if the acceleration itself is a function of time, okay? For those of you that know calculus, and it's fine if you don't, then you would end up with a situation where you have acceleration as a function of time multiplied by the variable, right? The only way to deal with that is the mathematics of calculus. But in the special case where the value a, right, the acceleration value, is not a function, but is instead just a constant, it's just a number, well, what you get is the equation of a line. Because what is delta v after all? Delta v is v final minus v initial. And then we can sort of rewrite this in a way to make it look like a particular equation, sort of make it look like the equation of a line, okay? So let me go over to here, here we go, where I will show you what I mean, okay? Because what we have is that delta V, by definition, is the change in something. The way we've seen this before is we've seen delta V just equal V final minus V initial, okay? That's perfectly acceptable notation, right? F for final, I for initial, using subscripts. We do that a lot with these labeling of things. Physics is a lot of labeling, okay? Just like in math, but here it's, it's a physical system, right? So math is so well suited to physics. It's a science that really just needs the most of that, of all these different variables, okay? Now, here's the thing though, that we want to instead refer to V final as sort of the instantaneous velocity. It's the function, right? So instead we'll write delta V as just V, right? Whatever is the current value of velocity. And then to give sort of special attention to the initial value, we'll call that V naught, okay? So here the 0 is kind of serving the same role as the I for initial. It's 0 for naught, which just means the initial, okay? So if we were to rearrange that, right, because all I've done is change the left-hand side of the equation and replace it with V minus V naught, right, which by definition is delta V, then I can just add the V naught, the initial velocity of both sides, and now I have a velocity function, okay? So this is a linear function for velocity specific to the very common important situation of constant acceleration. That's what we're talking about, okay? So this is a particular function that you can use if you know the value of acceleration, like the car accelerating, or something in free fall, right? Because in free fall, and we'll see this in the next lecture as well, that value of constant acceleration is none other than the value called little g, which is 9.80 meters per second squared. Okay, that's kind of the global average. It actually does vary into that the hundredths place of the meters per second squared. Okay, depending on kind of what continent you're on. Different density constants have slightly different gravitational acceleration. It's kind of a cool idea, but we'll talk about that when we talk about where gravity comes from. But the point is that the global average is taken as either 9.81 or 9.80, depending on who you ask. I think 9.80 or 9.80 is a good value to use, okay? Now you will also see gravitational acceleration sometimes rounded to 10. I'll always be clear on whether I want you to round it or not. I usually will not if you're in my class, okay? I think it's perfectly fine to not round it. There's only some cases where you might want to because the powers of 10 can be really clean for making a good argument, okay? Just a good example. Now, getting back to velocity though, in this idea of linear velocity, no matter what the actual numerical value of acceleration, the function for velocity as a function of time, okay, for this case of uniform or constant acceleration is a diagonal line because it is the equation of a line, okay? Now in this case, when this diagonal line passes through the origin, right, the intersection of the vertical and horizontal axes, the origin, well that happens, that's a common case, but actually if you look at the equation, it only passes through the origin when what is equal to what? Okay, I'm covering up part of it. When V naught is equal to V. Well, excuse me, 0. Okay, so this is only true when the initial velocity is equal to 0 meters per second. Because otherwise, the intersection with the vertical axis would be, say, at some other value, and that would be, because after all, V naught corresponds to t equals 0, so you have some other value of initial velocity. And then from there, right, with any numerical value of acceleration will always be a line, the equation of a line. Just that steepness of the line is going to change as the acceleration does, okay? Also, the line can literally point the opposite way, in other words, downwards. If the acceleration is negative, the sign matters, okay? Okay, but here's an example. How about an acceleration that is greater in magnitude and has a non-zero initial velocity might look something like this, okay? So this would just be the velocity function for some other velocity, okay? Still growing with time, a little bit steeper, and a non-zero initial velocity. Okay, but every single time it's the equation, the form of the equation of a line. And what I mean by that, for those of you that kind of remember this from a math class, it's the idea that y equals mx plus b. Right? So in this order, it'd be b plus mx. Okay, if you've seen this as an equation of a line, I just want to leverage that familiarity, right? Because what we're seeing is that y is equal to, this of course, the vertical value, okay? X is the horizontal value, Y is the dependent variable, X is the independent variable, and B is the intercept, okay? While M is the slope, okay? V naught, the initial velocity, is the intercept, acceleration is the slope, T is the independent variable, and instantaneous velocity V is the dependent variable Y. See it? Okay? So constant acceleration, uniform acceleration leads to a case, right, where we have equation of a line, we have a linear velocity. Okay? Right. Oh, here's another example of uniform acceleration. We'll get back to that one though. Okay, so what happens then to displacement in this case? So velocity is linear, displacement is parabolic. Okay, plain and simple. The distance at any instant, in this case, right, where velocity is growing linearly, is going to end up increasing with the square of time. Okay? Because you have this case where, if you think about it, there should be a non-linear increase because you're speeding up, right? So you're covering more ground each increment of time. So that means that the rate at which you're covering ground is increasing. That's what it means to be speeding up after all. So that means that if you're going to track displacement over time, which this graph is, right? Displacement or position as a function of time, it should be getting steeper. You should be covering more and more distance. You should be having a greater and greater position relative to zero as time progresses. Okay? That's what we see here. And it turns out the exact mathematical form is a parabola. Okay? That's why they make you study parabolas so much, because it's so important to constant acceleration, which is tied in with Newton's laws, hundreds of years of relevance. Okay? One of the most important laws for understanding motion. And a lot of people care about motion. Okay? Not just physicists. So, the distance traveled is equal to the area under the velocity graph. Okay? We've talked about that. In the previous lecture, I gave a good explanation, including talking about the units, or the physical dimensions as they're called, of the area under a velocity graph, velocity versus time, and why we know that that is displacement. Okay? So refer to that video if you like, but we'll take it at face value here. Okay? So for example, if it's linear, right? If your displacement is linear, then the area under the curve is just going to be, the area or rather if your velocity is linear, then you have a triangular area underneath your velocity versus time function. That area is displacement. Okay, so let's think about that then, right? So if it's a triangular area, what does that mean then about how much area is being covered, right? So if a car starts out with zero initial velocity, the final velocity is at the average velocity, okay, is 1/2 times AT, okay? So the idea is that because velocity is linear, and this was highlighted, although I didn't pay special attention to it over here, but it did in the previous graph. Okay, it was one of the things I kind of meant to come back to, was it shows here this V with a bar above it. If you've been reading the textbook, then you are familiar with this. This is average. Okay, in this case, average velocity. The bar always denotes average. So seeing the average here means what we're seeing is that it's 1/2 V. Well, V is just the final value at some corresponding final value of t. Okay, so what it's saying is that the average value is exactly 1/2 of that final value. How do we know that? Well, because it's linear. Okay, now to get this exact clean result, we need to have our initial velocity be 0, but it's still a really nice result, and it only applies to this linear relationship. Linear relationships are so incredibly kind of simple that they're incredibly desirable in terms of actually modeling systems using mathematics to understand the physical world. Now, they're also fairly accurate, as is the case here. Okay, so bringing that up, right? So we have, right, that average velocity is 1/2 the final velocity. Well, the final velocity is just whatever velocity you've reached after a certain amount of acceleration times time, right? Because we saw that the area under the curve of a velocity versus times function is displacement. Well, it turns out that the area under the curve of an acceleration versus time function is velocity. That's all we're saying, okay? You following me? That's all we're saying, okay? So let's go over to the one that had constant acceleration. I'm going to switch back over to here, right? So if we look at this graph right here, we look at constant acceleration. All I'm saying is that we have some elapsed time, so some t, initial to t, final, and within that time frame, from the time that the clock starts to the time the clock, hits stop, that area underneath the acceleration versus time graph, that area is going to be the change in velocity. The magnitude of that area is the change in velocity, okay? Because the height is acceleration, okay? The width is time. When you multiply acceleration times time, you get velocity. You get it from that linear relationship, right? Because v just equals v naught plus at. If v naught is 0, to keep things simple, right? Just set it to 0, then v just equals at, right? Therefore, delta v just equals at, okay? See it? Okay. So that's what we got. We got that area enclosed, that rectangular area, so very simple area to calculate and visualize, is just acceleration times time, okay? So, right, that's what we're seeing here, is we just replaced v with at. So we have that average velocity is 1/2 at. Okay. Well, then we go back to same argument as and this would be covered in the previous video, looking at a velocity versus time graph, knowing that the area under a velocity graph must be none other than displacement. Then we can say that d just equals v times t. Okay. Now, v times t implies that it's a rectangle, right? Because if it's some other area, you have to account for it, such as for a triangle, it's 1/2 base times height, which is precisely why we have it over here as 1/2 v. Okay, because it's 1/2 the area underneath. All right. So then how can we get away with here just making it a rectangle? Well, because it's V average. And V average is not going to change within the given time frame because velocity is linear. Okay? So it's cool because literally you get into something that you could derive with calculus, by the way. You can completely get to this point that I'm trying to get to with calculus. Perfectly fine. And it kind of justifies the most rudimentary use of calculus. But we're doing it just with basic algebra and understanding of graphs and just what it means to have certain axes, in this case with physical dimensions to them, okay, with units to them. All right, so average velocity is a flat line, just like constant acceleration, because remember, average velocity doesn't change, okay? So then it's just a rectangle. Average velocity times time is the displacement, okay? And we know that average velocity is just 1/2 at, so we can substitute it in, and we get that displacement is 1/2 acceleration times time squared. There's the parabola. Okay, that's remarkable. This parabolic shape right here, 1/2 at squared, okay? It's a parabola. It has that 1/2 that comes right out of the formula for the area of a triangle, okay? Pretty cool. And so that'll always show up in our formulas. That 1/2 is real, right? And it's not just there for some arbitrary reason. It's part of the math, part and parcel of it. Now, but the fact that it's proportional to the time squared tells us that the displacement grows more quickly as time passes, which makes sense because, after all, constant acceleration means we're speeding up. So, of course, we're covering more ground, as time passes because we continue to speed up, okay? And furthermore, we can extend this formula, right? And we'll do that with a little bit of hand waving, which just means that we won't kind of go back to the very basics and justify it. But one thing we did to make this explanation, which I touted as being so elegant that we could just use the graphs, one thing we did to kind of make it work was we remember we set the initial velocity to 0. I did that just a minute ago in the notes, right? So refer back to that. And we also set the initial position to 0. Now, can we generalize this and have a non-zero initial position and a non-zero initial velocity? Absolutely, okay? And it kind of makes sense. You can just add the position because, after all, that's what this is tracking. This is your position function. D is just wherever you are compared to wherever you started, like a race, okay? Now, as far as this fact that you can have the velocity start at some value other than velocity, we'll actually end up with another term, a term that would be familiar to those that remember the expressions for parabolas, because we're going to end up, or like the quadratic formula, we're going to end up with a term that has velocity times time. So we're actually going to have our variable, often time will be our variable, show up as t and t squared in different terms, okay? Now each term all has the same units, but you'll see what I mean in just a second, okay? All right, so here's that idea of extending the displacement to include non-zero initial velocities, all right? So let's see how they describe it here. Let's see, get this to not be cut off quite as much. So for a non-zero initial velocity, the total distance covered is the area of the triangle plus the area of a rectangle. Because, think graphically, right? I showed an example of this before. I said, well, it's always going to be a diagonal line, right? Velocity will always be a linear function when acceleration is constant. But where it crosses the vertical axis just depends on whether or not your initial velocity is 0. Okay? A lot of times we can set it to 0. Sometimes we can't, for whatever reason. Sometimes we just want you, students, to get practice with it not being set to 0. But whatever the reason, here we have an initial velocity not set to 0. So the total area under the curve here will be the triangular part, which we already justified as 1/2 at squared, and down here the rectangular part is just v naught times t, which actually you can pretty, graphically, it does show up pretty easily. You can see, right, because after all, the height is just literally v naught, units of meters per second. The width here is seconds, right, just, after all, the horizontal axis is time, and so there you end up with units of meters, right, because meters per second times seconds, seconds cancel, just got meters left. So, and it's a rectangle, right? So that actually is exactly how we end up with this other term, this v naught t. So you can see then that we now have a formula that works fine for finding how far you've gone relative to where you started, right? Because that's what this distance formula is giving us for any acceleration, okay, measured in meters per second squared, that's the A, and any initial velocity, okay? Now, we got some examples of it. So the velocity of a car increases with time as shown. What is the average acceleration between 0 and 4? Okay, so take a look at the graph. What's the average acceleration? Notice it's a velocity versus time function. Okay, think about slope. Okay, well, just 1 meters per second squared because the slope is 1. You went up by 4, in 4, so it's 4 over 4, rise over run, 1 meter per second squared. Okay, so the velocity of a car increases as time is shown. What is the average acceleration between 4 and 5? Much steeper section, still pretty straightforward. You just need to think about the rise over run. What value do you get? Make sure you can calculate this. Okay, so the difference, right? 12 minus 4, so basically you have that rise of 8 over a run of 1, so 8 meters per second squared. Pretty comparable to gravitational acceleration, okay? The velocity of a car increases as time is shown. What is the average acceleration between 0 and 5, okay? So just like as we dealt with averaging other quantities like speed and velocity, we don't want to take the average of the averages. Instead, we just want to compare the end point to the beginning point and the total elapsed time. So it's going to be 12 over 5, okay? Which, as a decimal, is 2.5 meters per second squared. Okay, that's the average acceleration over the entire time. Okay, so graphs, I've said this a few times, but I'm glad they say it too, right? Glad the textbook agrees with me that they contain a huge amount of information, right? Whether that's the velocity graph, which is great because you can interpret, displacement from it as well as acceleration, whether you're thinking about the area under the curve versus the slope, the tangent line. And acceleration graphs are no different. They can contain a ton of information. All graphs, right? You can get so much out of them in terms of thinking about their values of slope, the values of them changing from positive to negative, the values of them changing in terms of curvature even, which is something that we haven't really touched on that you're not so responsible for, but is just kind of in the litany of interesting things you can do with graphs. Okay? All right, so the last thing I want to do before we wrap up is just to do a numerical example with this constant acceleration. Now we're going to get some more practice, but this is going to be our last thing that we can do in this chapter. All right, so let's head back over to here. All right, I want to have a fresh page. Okay, so let's consider a car. We keep having that be kind of our go-to example. And so a car has an initial velocity of 10 meters per second, okay, on the freeway, okay? Then the car, because maybe it wants to pass a truck, is going to accelerate at 4.8 meters per second squared for 4 seconds, okay? Okay, so the car hits the gas, accelerates at a pretty big rate. This would be half of gravity, so you really feel it. You get pushed back into your seat with half your weight, right? That'd be a big acceleration. Okay, so the question then is, during that 4 seconds of acceleration, essentially, what's going to be the final like conditions, right? So I have 2 questions. One is going to be, what is the final speed of the car? Okay, I don't say after 4 seconds, but that's when the system ends. Okay, so it started at 0 seconds, ends at 4, right? And then the other question is, how far does the car travel? Okay, So I'm going to go straight to the formulas here. We've certainly seen the graphs. Oh, never mind. I'll at least put the graphs in a little bit. It's like, I might be belaboring the point, but no, we'll throw a graph in just because it only takes a moment. Okay? So the idea then is we're going to have a constant acceleration. Okay? So this is going to be our constant value of acceleration. This would be acceleration as a function of time, meters per second squared, over here seconds, and our value, which doesn't change, is just 4.8. Okay? Meanwhile, our velocity is going to be linear. Our velocity doesn't start at 0 because it starts at 10 meters per second, right? And then it's going to increase at a linear rate. Okay, the exact kind of value of the slope, I'm just kind of guesstimating here, but this would be velocity in meters per second. This is time in seconds. This is our initial velocity, v naught, which we know is just equal to 10 meters per second. Okay, we're at that linear function, that v naught equals, or rather v equals v naught plus at. So it'll be exactly this, v equals v naught plus at. Okay, now we didn't have an initial position, nor were you asked to worry about that. So your position graph, okay, which will only matter for number B, is going to be a parabola. Okay, we only care about how far you've gone in the 4 seconds, so we definitely set our initial value of position equal to 0. Right, doesn't matter to think of it as anything else. Right, and this is just going to be d in meters. This is of course again going to be t in seconds. This is our parabolic relationship. And our function here, right, is just going to be that however far you go in that elapsed time is just going to be v naught times t plus 1/2 at squared. Okay? So the fact that I gave you the time and I gave you the initial velocity and I gave you the acceleration means that this particular version of this uniform acceleration problem is clearly in the plug and chug category, which is a great place to start. Okay? So what we do then for part A is we'd say, okay, well, we just want to find the final velocity, okay, which is the instantaneous velocity after 4 seconds, and it's just going to be v naught plus at, or here it's going to be 10 meters per second plus 4.8 meters per second squared times 4 seconds. All right, so over here, I'm just going to go ahead and plug that in. So it's just going to be 10 plus 4.8 times 4, because I can't do that in my head. And we get 29.2 meters per second. So we more than doubled our speed or velocity, if we care about the direction, but we more than doubled that value within the 4 seconds. Okay? So it's a significant increase, right? Because the acceleration is an extra 4.8 meters per second, and so we had 4 seconds of that. So if you think about it, right here is essentially 4 times 4. And then some. So in other words, this product right here is greater than 16. So 10 plus 16. That's right. That's how we're getting something greater than than 20 essentially. But more than doubled. Okay. Okay. And then finally in part B, we would just want to find the final position. So then D is just going to be v naught times t plus 1/2 at squared. That's just how far we've gone during our 4 seconds of acceleration. So then we'll just put in our 10 meters per second because it matters how fast you're going initially, and then times 4 seconds plus 1/2 times 4.8 meters per second squared times 4 seconds and then square it. Okay, so let's go ahead and plug that over here into our calculator. So we got 10 times 4, okay, and then plus 1/2. All right, times our acceleration value of 4.8, and then times 4 squared. So 78.41 meters. Okay, you still see that? Yep. So 78.4, right, meters. That's how far we go. That's how fast we're going. All right, those are the 2 questions asked. Okay? So hopefully that really illustrates some of the things you can do here with a use of this particular equation justified graphically, describing a very important situation of constant acceleration, which we'll learn comes from a constant force in more detail later, and will tie in with the very relevant situation, real-world situation of free fall in the very next chapter. Okay, so that's it for chapter 2. I hope this has been interesting and informative. Thank you so much for watching these videos.